Okay, I'm going to move pretty quickly through this material about chapter 9 in our textbook because I bet you've covered it with a little bit more depth in physics, but I want y'all to know what parts are going to be important for examination in this class. So the big things here are coherent scatter, like we've already said, is classics, or Compton scatter, could also be called Rayleigh scatter, Compton effect, photoelectric effect, pair production, photodisintegration. That's what we're talking about. So coherent scatter. We've said that this predominates at higher energies, right? And that's significant to us because it's independent of the atomic Z number, right? I'm sorry, coherent scatter. I apologize. This is page 149 in our textbook. Coherent scatter, also called classical scatter, also called Compton scatter, also called Rayleigh scattering, right, is the stuff that predominates at the low energies of the X-ray tube, the low energies of the X-ray tube, and it's of little importance to diagnostic radiography. Basically, all I need to know is this is the one I don't really need to know, right, even though it still has a C in it. But in this, a photon comes really close to the nucleus, does not ionize the atom, and goes off in a different direction. And generally, it's important to know this about coherent scatter. The angle is very small. And one of the things our textbook points out is this is the reason that sunsets are red, right? Is because of coherent scatter, also called classical scatter, etc. Is it's a small angle scatter, which is like red light on the visual light spectrum. Compton scatter. Okay, this one is important to us, right? And the big thing that we need to talk about is it does not depend on the atomic number of the atom involved, right? Compton effect can happen regardless. So it does not matter if it interacts with a bone or lung or whatever, Compton scatter, right? So the big thing is once we get over like a certain level in the energy of our X-rays, Compton effect starts to take over, right? And since it's not dependent on the Z number, all it's going to contribute to is fog on our X-rays. Okay? But in Compton effect, what happens is a photon knocks an electron out of orbit. A lot of times it's an outer shell electron, and it imparts a little bit of energy to that electron, kinetic energy to the electron, but it maintains quite a bit of its energy, goes off in a different direction. And the important thing with the Compton scatter is it can occur in any direction, right? So we said that Compton effect is also the primary cause of occupational scatter. So my primary dose for as an X-ray tech comes from the patient. I'll say that one more time because it's very interesting. Most of your dose as an X-ray tech will come from the patient, scatter off of the patient, because the Compton effect can happen in any direction. So we might call it forward scatter, which would actually interact with the image receptor and create fog on our image, or we might call it side scatter or back scatter, and that way it's coming my direction, right? If I'm standing there by the patient. Photoelectric effect. We've said that we really, really like this one because it's directly tied back to the atomic number of the atoms, right, as well as the tissue density. So it results in a total absorption of the X-ray photon. Like that X-ray photon just stopped, and it imparted all of its energy to that electron. We're now going to call it a photoelectron, right? This is actually the reason why Albert Einstein won the Nobel Prize. It was not for theory of relativity, it was for photoelectric effect, because this has a lot of applications even beyond X-ray. This is, for example, how night vision goggles work, is exploiting the photoelectric effect. So, the big thing here is that the probability of photoelectric effect is directly proportional to the third power of the atomic number of the absorbing material. So it's tied back to the atomic number of the absorbing material. This is on page 151 in our textbook. And so this is why we have diagnostic X-rays. It's photoelectric effect, right? Now, one other thing that I want to point out about the photoelectric effect, I don't know that our textbook talks about this, but your physics class, you definitely should, is a related thing that is spelled like auger, but it's pronounced like Auze. Right? Have y'all talked about this? Auze, right? So in the Auze effect, after a photoelectric interaction, that knocks this K-shell electron out. One of these outer shell electrons, they're lazy, and they want to jump down here. And so that produces another photon, right? It will be characteristic of the energy difference between those binding energies in this Auger effect. And where things Auger effect gets really crazy is now we have a vacancy here. Well, one of these guys might jump down and say, hey, I want to be down there. Now we've got another one. So it could be like a cascading effect where because of this Auger effect, more and more characteristic X-rays are being produced. So the thing I want to stress here, and I think this is one of the reasons that people get confused between like Bremsstrahlung and characteristic and all that kind of stuff. We said that Bremsstrahlung only happens inside the X-ray tube, right? The other thing that happens in the X-ray tube is what? Characteristic X-ray production. Well, right, guess what? Characteristic X-ray production can also happen inside the patient. So that's a point of confusion for people, right? In this instance, we had this Auger effect that produced characteristic X-rays. So each one of these X-rays that occurred by this Auger effect is a characteristic X-ray. I want to emphasize, though, this is not describing photoelectric effect. So we had initially the photoelectric effect was just photon knocked a K-shell electron out and stopped. It ionized the atom and stopped. That's photoelectric effect, period. But then we said some interesting stuff could happen where we have electrons falling down into that inner shell and producing characteristic X-rays. And we're going to call that cascading event the Auger effect.
What does that say on the top?
Characteristic. I'm sorry. Characteristic. Yeah, I know. So each one of those X-rays that were produced by the Auger effect is a characteristic X-ray. And why did we say it's called a characteristic X-ray? Why is it characteristic? I think Talia said it. It's characteristic of the binding energy of that electron shell. So it gives up some of its energy to drop to this weaker shell, right? And that energy that it gives up in the form of a photon. So it will be very specific to that atom, though. It will be a characteristic of that electron binding energy of that atom. Pair production. This one is of interest to us when we're doing PET-CT, and this is the reason why we don't use the PET-CT bathroom, is because we've got pair production going on inside that toilet, right? This is where an incident photon has sufficient energy to destroy a neutron. Or I take that back. Yeah, to destroy a neutron. To destroy a neutron. In doing that, it does something really strange, right? It produces both an electron and a positron. What the heck is a positron, right? Like you don't see that anywhere spinning around any atoms on any test. It is actually a form of antimatter, right? Antimatter. What does antimatter mean? It means it destroys matter, right? It does not like matter. So some folks like Richard Feynman have even said that it is possible that a positron is an electron traveling backwards in time. So this is weird stuff that's occurring now. Bear in mind, thank God, this is not happening in the diagnostic range of X-ray energy. This requires at least, I'm trying to remember, it's 1.02 megavolts, mega electron volts of energy. I'm trying to remember the exact amount of energy that's required to produce this. Bear with me. For pair production. Let me pause. So this, yeah, it's I think it is 1.02 mega electron volts. We are not working in the mega electron volt range of energies. We're working in the kilo electron volt range of energy. So this is like close to like 10,000 times the voltages that we're dealing with, right? Or I guess technically 100,000 times the voltages that we're dealing with. at this energy range, it has the ability to produce two separate particles, each having 0.51 mega electron volts. Where did that come from? Well, it's precisely half this energy right here, right? So one of them just careens off. It's an electron. It might go off and bounce around and find an atom to enter. But the other one I mentioned is a positron. It is a form of antimatter. It will collide with an electron, destroy itself and the electron, and produce two photons, both of them having a ton of energy, right? And the reason I'm stressing this is, number one, we do not get to play with this stuff, which I'm grateful for. Number two, don't use the PET-CT bathroom, because number three, this is what PET-CT is. This is what PET scans are using.
Is that 1.0 K?
Yes. Annihilation. It's annihilation energy. Yeah. So does that divide right? It doesn't, does it? Okay, I can't do the math right now. It's too late in the afternoon. But I believe that's the correct amount of energy. I know that it is correct. Okay, then these are definitely correct. So we're talking about anything over 1.02 mega electron volts, 100,000 times the amount of energy that we're using. Okay. Photodisintegration. This is anything over 10 mega electron volts. That photon could bombard the nucleus, actually knock a nuclear fragment out of the nucleus. I have no clue what a nuclear fragment is, but it doesn't sound good, right? So, again, the big thing here doesn't happen within the diagnostic range of energies. It could potentially happen in radiation therapy or nuclear medicine. Let's talk a little bit about differential absorption, because this is how we're able to make the pictures that we make. So, differential absorption is what we're talking about when Compton effect, photoelectric effect, and also some X-rays just going through with no effect happens. And the difference between the X-rays that are transmitted through the patient, down here we see transmitted X-rays striking the image receptor. The difference between the transmitted X-rays and these X-rays that are either Compton scattered away from the image receptor and the photoelectric effect where the X-rays are just completely attenuated and the patient's cells are ionized, that difference is how we get a picture. So we will call that difference differential absorption. And the interesting thing, because of its tie-in, because photoelectric effect is tied to Z number, differential absorption will increase as KVP is reduced, because it's exploiting more of the photoelectric effect. We said at the lower energies, photoelectric effect predominates. There's some Compton scatter that occurs, but photoelectric effect predominates. When we get to the higher energies, the photoelectric effect is not as prominent, and the Compton effect starts to predominate. So the differential absorption will increase as the KVP is reduced. This is a box on page 155 in your textbook. Page 155 in your textbook talks about that. Okay. So one of the things that we consider for diagnostic X-ray is the interaction of X-rays with tissue is proportional to the mass density of the tissue regardless of the type of interaction. I'll say that again. The interaction of X-rays with tissue is proportional to the mass density of the tissue regardless of the type of interaction. Okay, so it doesn't matter if I'm talking about Compton effect or photoelectric effect. The mass density, like the amount of, say I'm X-raying the 400-pound person at DeSoto, right? I hate to pick on DeSoto, but that seems to be where they live. That mass density of this patient now that I am trying to get X-rays through, right, is going to have direct bearing on how many X-rays get through, period. A lot of them are going to be lost to Compton effect. Some of them get lost to photoelectric effect. I don't care. The patient just stopped them by how big they were, right? So there are some patients who get so large that it is very, very difficult to X-ray them. You've probably already encountered that to some degree.
I was told that there's people that, it will break the table, so
Yes.
they had to send them to the zoo. Have you ever heard that?
Zoo and
It's not a joke.
no, it's not a joke. We used to send people to SeaWorld. We used to send people to SeaWorld. Yeah. Because of table limits and also, the
I thought it was a joke. They were being dead serious.
no, they're dead serious. They have tables that can accept like a weight limit over 400 pounds, right? So there's like a whole new field of nursing that's coming out called bariatric nursing, because there are specific things needed to image to treat folks who have who suffer from morbid obesity. So again, this is just a nice list of these factors affecting this differential absorption. I said that high atomic Z number. Which one's affected? Well, the photoelectric effect, right? Compton is not affected by Z number. So I don't like Compton. This is actually a really helpful little slide. Increase KVP. As I increase the KVP, my photoelectric effect stops, right? Compton scatter will start to be proportionally greater. So now it will be the primary thing driving differential absorption. Increased mass density, so that bigger patient. I might see an increase of both photoelectric and Compton, right? I'm going to have a hard time just getting these X-rays through that patient. Now we're talking about sending them to the zoo, right? I hate to put it, but that's what that is saying. Here it is in a chart form. Let me move this chart away. So it's just the same material, just represented now graphically. Maybe some of us can, this is easier for us to understand. But PE increases, so it's not pulmonary embolism in this case, it's photoelectric effect. Increases with high atomic number, right? How increase? This arrow is not correct, right? It will decrease with an increased KVP. It will also increase with a higher mass density of the patient. Compton scatter doesn't care, doesn't give a rip about Z number, right? It's just coming straight out of Compton. As KVP increases, we will see the Compton scatter increase. As the mass density increases of the patient, we will also see Compton effect increase. Transmitted X-rays. With a higher atomic Z number, we will see a decrease in transmitted X-rays. With a higher KVP, we will see an increase in transmitted X-rays. With an increased mass density of the patient, we will see a decrease in transmitted X-rays. X-rays exiting the patient. Sometimes it's also called the remnant beam, right? Transmitted X-rays, the remnant beam, whatever's exiting the patient.